We're going to learn, I don't know, kind of a new trick. How to integrate getting volume. We're going to learn the first of a number of techniques that we obviously will not cover, but this is the most useful one. If you had some kind of solid, did I draw that right? And you know the area of a cross section. You could break this up into slices, lots of tiny slices, and each of these slices would have some small, and so you can just multiply here, but integrate. So instead, you have, some other more complicated shape. And again, you kind of slice it up. Again, you really just need to know the area. Now, if instead of being nice and uniform like this, you have something where the area of the slices change. Area 1, area 2, 3, area of X. Then you can think of this as having little tiny slices, and in each slice, you know the cross section. So you can integrate from one side to the other, the area function, and that will give you the volume of that you're looking for. So that's the main strategy we're going to look at here. Well, this gives us the ability to do some things we have been able to do, we might know. If I were to have a sphere, radius r, I think many of you may know that the radius is 4/3 pi cubed. I think it was the Greeks figured this out. You stop something I can't pronounce. You stop the D's. Something you use the method of exhaustion, but we have a more direct way to do it now. So let's just take a look at the central cross section here. There's our radius, and here's X. So the height here is going to be using the Pythagorean theorem, square root of r squared minus x squared. And now the idea is we have a sphere, and you think of breaking it up into little almost cylinders. They're make that kind of a curved edge, but make them kind of small. This is, you can think of this as dx, you can get them as infinitely small. And so what we're going to do is negative r and this is r. So we want to integrate from negative r to r this area function. Okay, what's the area of one of these little circles? Well, if the radius on each of these is, I don't know, I'm going to call it little r, but that's what we decided. Little r is square root of big R squared minus x squared. I don't want this to be too confusing. Little r is a variable, big R is a constant, whatever radius of our sphere is. And we know the volume, the area of this little thin little disk is pi r squared. But r we know is square root of r squared minus x squared. So it's going to be from negative r pi times r squared minus x squared dx. All right. That's pretty straightforward. I don't know if I've introduced this to you before. This is a technique that simplifies some integrals. If you know something's symmetric, and you're going from negative a to positive a, you can take the pi out here. You can just go from 0 to one end just by multiplying it by 2. It's symmetric. All right. So we have r squared minus x squared. All right, well, let's find the antiderivative. We're going to have r squared x minus x cubed over 3 from 0 to r. All right, so that's 2 pi big R cubed minus r cubed over 3. Not yet. Minus, 0 minus 0. Okay. Well, r cubed minus 1/3 r cubed is what? That's 2/3 r cubed times 2 pi gives us our 4/3 pi r cubed. So now this mysterious formula that you've just been given up till now it has derivation using calculus. Okay, it's nice to know. We have a lot more, lot better tools in our toolkit. Any questions about that? All right. Let's take a shot at something else we might not know. Might not know how this comes about. The question I have is, what's the volume of a cone? Has a height, has a radius, and volume of a cone, you probably know, is what? Let's take the volume of a cylinder, pi r squared h times a factor and a third. So let's see if we can derive that. So let's say we're going to put our cone sideways here with the x-axis kind of coming down the center. So we have these little circles here, or little cylinders, I guess, that each have a height of y, right? So the area of each of these circles is, of course, pi y squared. So this is our area function. So we're going to integrate from 0 to our height, whatever that happens to be, our area function. And and we can see our area function is, again, is the y coordinate, or if you like, it's this function. So pi f of x squared dx. So now we just have to find out what this function is. Any thoughts on that? Seems to me this is just a straight line. It goes through 0, so its intercept is 0. So we just need to know the slope. Let's see what the slope is. That's our delta x. That's our delta y. That's the height here at the bottom of the cone. Well, that's our r. So the slope is delta y over h x. All right, we could plug that in here. And we have some constants here we can take out. And now we have a fairly simple integral to handle. So it's going to be h cubed over 3, 0 to h. And I think you can see pretty quickly this is going to be I r over h cubed. Well, I did something wrong. Nice. Oh. R squared, h squared. That looks a little better. I r squared, h over 3. Okay, so that's again our mysterious volume of the cone. All right, let's look at something that you might have seen in a homework. We were doing homework on this. Maybe not as useful, but. So we have a function f of x is the square root of x. Well, what does that look like? This. And you want to spin it around the x-axis. Something like that. And we want to find, given some, we uprighted it, call that h. We want to find the volume inside this thing here. So again, the setup is pretty simple. We're just going to integrate from 0 to h the area function. That will give us our volume. So we just have to figure out what the area function is. So here again, we have a circle. Its radius is going to be f of x. And the area is going to be pi times x squared, just pi r squared. So we plug this in. Times f of x squared dx. But f of x is square root of x, so turns out easy problem. Easy integral. So this just turns out to be pi 8 squared over 2. Sometimes you run into a problem where this general strategy runs into a little nit. You take the function f of x equals x cubed, here. And we want to rotate this around the y-axis. And we want to find the volume from 0 to 8. It'd be problematic to try and integrate it along the x-axis. But there's no reason you can't switch the roles and integrate along the y-axis. Clearly, I integrate from here to 0. Question is, what do I integrate to? Well, f of x equals x cubed. Is equal to think about this. So somewhere up here I have right? I'm sorry. So the problem states, that's why I'm confused, states we want to integrate from 0 to 8. And again, I'm not sure. Yeah, 0 to 8 on the y-axis. Okay, well that's fine. The catch here is, you know, if y equals x cubed, my radius here is x. So I have to figure out what x is. Well, this is obviously cube root of y, or you prefer y to the 1/3. So integrating along the y-axis from 0 to 8. Now dy, because we're going along the y-axis. My area function with respect to y. Well, if x here is cube root of y, the area of these circles is going to be what? Pi y to the 1/3 squared, or pi y to the 2/3. So that's what I want to integrate here. again, it's not a particularly challenging integral. When you finally look at it. Pi y to the 5/3 over 5/3. 0 to 8. We have to think a little. How do I get 5/3 of 8? Well, cube root of 8 is 2. 2 to the 5th is 32. So 3 times 32, 5 over 5, or 26 over 5 pi. So the point here is just that if you need to, it's better, you can just integrate up along the y-axis if that's the way the problem is given. There's one more kind of generic problem I'm going to go over. We'll do something that's kind of interesting. This problem is often referred to as a washer. So we have two curves here. We have y equals x and y equals x squared. And we're interested in the area here, but what we want to do is we want to spin it around the x-axis. So, circles here. This, but the center of this is kind of hollowed out. I can draw that very well. So you just have these, two pieces. Well, it's not two pieces, just this piece. So, what then to make of the area function we need to find? Well, starts off at a point, of course, and then it's a ring, and then the ring gets thicker. And then eventually up here, the ring gets thinner. And then eventually we end up with this kind of edge over here. So the problem isn't really different. The trick is just we need to find this area between these two rings. So we need some way to describe them. Well, the outer ring, the outer curve here is just x. And the inner curve is x squared. And that's, so we can take that as our, a little differently. Our outer ring has a radius of x. It has an area of pi x squared. The inner ring has an an area of x squared, its area is pi x to the fourth. So that's our area function that we're going to integrate. Now, where are we going to integrate from? Well, we're going to integrate from 0 to where two functions are equal. So we have x squared minus x equals 0, or x times 1 minus x equals 0. So clearly, the two boundaries are going to be 0 and 1. And again, it's not a difficult integral. It's going to be pi times x cubed over 3 minus x to the 5th over 5 from 0 to 1. So that's just pi times 1/3 minus 1/5, which is 2/15. All right, so that's how you do these volume problems. There are other types of volumes that don't succumb to this method that we're not, like I say, if you go on to Calc 2, we'll do more with this. Now, it seems like we're going to get done kind of early today, but before we do, I have something to do with this that I always found really interesting and curious. It tells you that while mathematics is often a good model for some physical things in the world, one has to be a little circumspect about that. There's a branch of mathematics where you run into these things a lot. It's called analysis, and I'm just going to show you some things you know from analysis that are really odd before we see something from calculus that's really odd. So if I have a function x minus 1 over x minus 1, so we graph that. It kind of looks like this, and then kind of draw a little circle there. And we might say, well, there's a hole in the line. Well, I mean, this is just artificial. We just draw that, and that's what we need. So, what do we mean by there's a hole in the line? I mean, how big is this hole, right? I mean, if 1 is right here, well, how close can we get to 1 on either side? How close can we get to that point? As close as you want. I mean, if you say, well, you get 10 to the minus 100 centimeters. You get 10 to the minus 200 centimeters. You just keep going. There's no end. So while we say there's a hole in there, there's not enough room to get anything through. It's just this peculiar thing about real numbers. You can take this a couple steps further. What if I have a line and x equals 1 if x is irrational? X is 1 if it's rational. undefined. It's rational. In other words, wherever there's a fraction here, you just take it out. It's one of these holes. That's a lot of points we're removing. That's an infinite number. And again, you take a look, where are the holes? Any, like if I say like 1/3, how big is this hole with 1/3? Again, it's now, the rationals and the irrationals are really different. But it turns out if you switch them here, you just don't define the irrationals and you define the rationals, all the fractions. It turns out you have exactly the same problem. It's just, you can't, you can find some place to get through, like 1/3, but the room around it is nothing, it's 0. Well, now's a point where it's even stranger. With the tools we have here, if I wanted to integrate from, say, 0 to 1, make it easy, they don't work. We're using something we would call a Riemannian integral. But in higher math, we define a different kind of integral. And we actually can integrate across here. And it turns out that if you integrate, f of x equals 1 for irrationals from 0 to 1, you get 1. But if you do the same thing with rationals, you get 0. It's kind of like, even though between every rational is another rational, we call it dense set, somehow it's kind of vaporous. It's like dust. Doesn't really amount to anything. Whereas you can see that what's really filling up this measurement here is the irrationals. All right, so that's just this peculiar thing. And I bring it up just because I want to make clear that in mathematics, sometimes if you try and transfer them over to some kind of real world situation, it doesn't work anymore. Mathematics is kind of idealized, and you're just kind of stuck with those results. They're just live in this alternate universe. All right. So that being the case, I want to show you a problem that it defies logic. It's the result. What we're going to do is we're going to look at this function f of x equals 1 over x. And we're going to integrate it from 1 to infinity. Well, not exactly the function. There are two functions we're interested in. One comes right out of today's lesson. We take this, and from 1, we're going to rotate it. Rotate it around the x-axis. So that's going to be the volume. So let's take a look at this. How do we do this? Well, again, the area function. We're going to have an area function. And the area function here, well, it's just y, or 1 over x. That's our bar. So it's going to be 1 over x pi 1 over x squared. I don't think we've emphasized integrals that go to infinity very much in this class, if at all. And to do them right is not very hard. You just have to kind of rewrite this as a limit. So we rewrite this as the limit as some number a goes to infinity of 1 to a pi over x squared dx. We just have to separate the inclusion of infinity here as a limit. Although as a practical matter, when you evaluate this and you get 1 over infinity, that's 0, and if you get infinity, well then you have a very large number. All right. So what is the antiderivative of, take the pi out also, of 1 over x squared? Anyone? Should be a simple question. Just asking for the definite integral of 1 over x squared. Yes? Plug that in. Left limit, say, approaches infinity of negative 1 over a. This is 1, sorry. Minus a minus 1. So limit as a approaches infinity of 1 minus 1 over a, and I think that's pretty obvious what this is equal to. A gets bigger and bigger, this gets smaller and smaller, this just becomes 1. So that's nice, we've got this tube, it goes on infinitely, but if we could kind of turn it over and pour some kind of liquid in it, it would have a volume of 1. That's not where the head explosion moment comes yet. What we want to look at next is the surface area of this tube we defined here. Okay, we have to think about this. We haven't done this kind of problem, but it shouldn't be that hard to kind of figure out. If we have these, think of these as these little pieces here that are getting smaller and smaller. They have some tiny width dx. They have, they're like little cylinders. They have a radius of y, which of course is run over x. So, okay, the radius is 1 over x. Well, what's the circumference? It's going to be 2 pi r, right? Or 2 pi times 1 over x. And then, the width, whatever it is, dx. And again, we want to integrate this to infinity. So again, we want to do this right, and just say the limit as a approaches infinity, the integral from 1 to a, 2 pi over x dx. So again, we take the constants out. What's that? What's the antiderivative of 1 over x? ln x. I want to write all this other stuff in here so we don't lose it. So we have the limit as a approaches infinity, 2 pi times ln of x from 0 to a, 0 to 1, 1 to a to 1, 1 to a. Okay. So let's bring this up here. Limit a approaches infinity, 2 pi. So the ln, we get the ln of a minus the ln of 1. The ln of 1 is, we're going to call got like 10 to the 1 is 10, 10 to the 2 is 100. 10 to the 0 is 1, 10 to the minus 1 is 10. So the log to the base 10 of 100 is 2. Log to the base 10 of 10 is 1. Log to the base 10 of 1 is 0. Log to the base anything of 1 is 0. So I end up with 2 pi times the limit a approaches infinity log of a. What's that? How big is that? What happens to the log as you get bigger and bigger? Keeps growing. Not a number, it's infinite. Wait, let's go back. So I have this tube. We're going to fill it up with fluid, a finite amount of fluid. Right? It's got a finite volume. But if I want to paint it, I'm never going to have enough paint. Isn't that strange? It's just one of these things that happens in math. Lost the cap here. All right. Well, that's that's today's lesson on volume. Hope you like the little ending. I don't have any more material for today, so if you have anything you want to talk to me about, I'll hang around. So.